Welcome back to another episode of The Observatory. I'm your host, Kyle from Bigeye, and today we are talking with Dan Shiebler from Abnormal Security, where he is the head of machine learning and leads the detection team. Dan, welcome to The Observatory.
Thanks, Kyle. Happy to be here.
Abnormal does some pretty cool stuff in like threat detection. They work with some pretty exciting companies like I think I saw Splunk and Xerox on there. Some of the world's largest organizations are using Abnormal. I'm not from the security space. I'm sure plenty of people watching are not either. Dan, could you give us just like an intro? What does Abnormal do? Why is that important? Why are companies like this working with you? And then what does the detection team do within that?
Absolutely. So Abnormal Security fights cybercrime. We do this by detecting cyber threats coming in through messaging applications or through compromised accounts. Our primary product is email security, detecting and mitigating threats like phishing, vendor fraud, ransomware, business email compromise. Essentially, threat actors will send malicious messages or compromise accounts and try to take steps to increase their access, increase the amount of damage they could do to organizations in order to either get credentials and exploit them or install ransomware or apply a number of other malicious actions. The Abnormal Security product functions by detecting and mitigating these kinds of attacks. And the detection team utilizes machine learning, artificial intelligence, data science in order to identify these attacks, distinguish them from normal business behavior, and mitigate them effectively.
And so sounds like detection team, your role within the org is lead, like given a bunch of these inputs, I assume you have information like who is the user's inbox that we're currently looking at, what's the body of the email, who's the sender of the email, et cetera. Those are all inputs. And then I assume from that, you're producing some threat level or categorization or warning, or what is sort of your team translating from on the detection front?
Yeah, exactly. I mean, we can ultimately think of this as a very fundamental classification problem. In a lot of ways, this is a very classic ML problem. You have a particular message or a particular account, and you want to determine whether or not this message is an attack or this account is compromised, given the information that we have about this message or this account. And this requires collecting as much data as possible about who is the person who's receiving this message, who is the person who's sending this message, what is their historical patterns of behavior, and how is this different from what we're observing here? What are all the different indicators of compromise that might be attached to this account sign-in event or to this message event? And how do those indicators of compromise compare to things that we've seen in the past?
Okay, so bunch of different signals here, and are you're processing these sort of like in real time? So like an email comes in, and then you guys need to have this pre-trained algorithm. You're going to feed the email through that, and then you're going to get a warning. Is that surfaced directly to the user? Do you guys block the email from going into the inbox, or what's sort of the result from the model?
Yeah, that's a great question. So there's actually a bunch of different results depending on our customer integration. Different customers have different security teams, different degrees of sophistication and desire for control over what kinds of communication and behaviors to apply. The default is what we call an API-based solution. So basically, when there's a sign-in or an email, we receive a notification, and we can take action to pull that email or to block that sign-in ourselves, and then surface the information to the customer security team to take further action. But there's a wide range of different kinds of remediation actions that we can take, from just moving a message to a different folder, to tagging it with a banner, to presenting a notification to a security team without notifying the customer based on the size of the security team, the circumstance, the business, the judgment of the risk level, et cetera.
Okay. And how large is this team, and what's the sort of mix between, let's say, like data scientists, or I think, we talked a little bit before the show and you mentioned that there's a mix of software engineers, traditional software engineers, machine learning engineers. What does it take team-wise to essentially build this product?
So the team as a whole is about 40 people. And that splits between people who are a little bit more traditional back-end software engineers, machine learning engineers, and data scientists. And there's rather than focus on the individual roles, I think it's helpful to explore the kinds of problems that come when we're building this kind of system. There is, of course, a tremendous amount of data to process to be able to understand not just what's the context of this individual email and be able to consume it and process it and take action on it fast enough, which is itself a very difficult problem, but to accumulate all the information about historical emails and incorporate that into the judgment of what to do on this particular message. For example, messaging often takes place in conversational threads. It's important to know what has happened in all of the threads leading up to this particular message when judging whether or not a particular message might be a invoice fraud or a conversation injection. A very common type of attack, for instance, is someone compromises an account and then tries to leverage ongoing threads into attacks. And so detecting that effectively requires having access to these previous messages that were recently processed when making this judgment. And so that's a difficult back-end engineering challenge of processing each message in a way that you can make them available to future processings in an extremely low latency fashion. So there's a lot of intense back-end engineering that powers that. And then there's, of course, machine learning engineering and actually building and deploying machine learning models, training machine learning models on the new data that we see, and data science. There's a humongous range of different kinds of understanding the performance of the models that we're deploying, understanding how to optimally tweak the parameters of the system in order to adapt to each of the different customers and understand when things are going well and when things need to be improved.
And okay, so you mentioned models in the plural. Or I mean, it sounds like there's not sort of like one mega model that can handle all of this. Are we talking about distinct models for like different types of threats that you need to process, or do you have different models for different customers, or what is the sort of landscape of models that your team actually owns? What does that look like?
So there's models for different kinds of threats, certainly, and there's certainly models like we could think about models broken down at a number of different levels. There's of course models that are broken down at the level of what's going on accounts and sign-ins and what's going on with emails and messages, and then different kinds of messages as well. But within even like the realm of messages, models break down in many different ways. We have general centralized models that try to solve problems like, is this an attack or is this safe at a very, very high level? But we often find it valuable to build submodels that dig into individual subcases. For instance, the characteristics of an attack when you're looking at a sender that's never been seen before, something that's coming in completely from the outside, is very different than when you're looking at a vendor who's been compromised. A vendor who's been compromised, the type of information that you have to use to make a decision is very, very targeted. You need to look not just at what's the normal characteristics of an attack, but specifically what's the characteristics of this vendor and how is that different from what we're seeing now when trying to determine if this is a vendor compromise. And so given the degree of difference between the types of signals that we want the model to take optimal advantage of, we often find it valuable to break down into individual submodels of different attack types. So there's this at the level of each individual attack type, we have different kinds of submodels to handle it, as well as general ensemble models that try to make general decisions. We take a very defense in depth approach towards being able to drill down into the most important and most vicious kinds of attacks.
Got it. Okay. And do you have sort of ensembles layered over all of that ultimately, or do models drive individual features? For example, like you mentioned that you could pop a banner, there's all these different actions that could be taken. Are you sort of architecting like, okay, this model can drive this specific feature or response, or is everything sort of trying to fit under like a larger umbrella or like an abstraction of some sort?
So we can think about things as feeding into a detection layer, where the detection layer makes the final decision of whether or not a particular input should have an action taken on it, should have remediation action taken. And that decision, you could think of it as sort of a big or, where it's a giant or statement over any of the individual detectors that are individually equipped to make this final decision of, yes, this is bad, we should take action on this. And of course, there's the case that as you add more and more detectors, you run the risk of decreasing your precision and decreasing we have extremely high precision requirements in order to produce a customer experience that doesn't require security teams to spend hours looking for missing messages and locked out accounts. So we need to hold ourselves to extremely high precision. So we need to be very careful when we add new detectors or modify detectors to maintain this precision. But ultimately, each individual kind of detector feeds into this general or statement. Certain detectors are ensembles of lots of different models. Certain detectors are a single model that's generally itself equipped to make a certain decision. Sometimes one detector is a individual model that says if this model's prediction is at least some very, very large number, then we're confident enough to make this decision. But a different detector might take that model as an input into a more general decision and be able to take action even if that model happens to be less confident. Sometimes this will happen a lot if you have a individual model that looks for a particular pattern, but attackers modify that pattern very frequently and try to get around it. So we have general ensemble models that will look for a more general combination of different attack types.
All right. So you kind of have a fairly large portfolio here that your team is responsible for maintaining. Anything in, and we'll talk about this in a moment, but you have a background at Twitter as well, working sort of on problems at scale there. Anything specific that you've learned about the management of this many models? Obviously, you're working in an environment that's sort of like constantly changing and evolving. So I assume that there's quite a lot of effort kept in like keeping those models up to date and reacting to the world and the way it's changing. Anything specific that you've learned about what it takes to manage a portfolio that large of that many models and sort of keep everything sort of fresh and up to date?
So one thing that I've gone back and forth with, both at my time at Twitter and my time here at Abnormal, has been how to think about the complexity that exists in a modeling stack, and what are the kinds of complexity that are malicious, and what are the kinds of complexity that's benign. If we have 100 models all in production, but there's only 3 or 4 of them that we're constantly thinking about and seeing issues from, then it's only really those 3 or 4 that are the complexity that people need to think about. If the other models are running independently and not feeding into each other and performing with high enough precision that they don't need to be taken down, then they're not actively contributing to the complexity that people are managing. The main thing that is the key to this is monitoring, and monitoring the precision of each individual detector on its own. For this type of federated system where we have each of these individual detectors operating independently and capable of making a final decision by themselves, what's critical is understanding what is the criteria for keeping a particular detector live. If you launch something and keep it live as long as its precision, the unique precision of this individual detector is high enough, and then take it down as soon as that precision drops. What you've done is largely separate the complexity of this detector from the complexity of the other detectors. This is a strategy that makes sense when we have teams of certain size moderate controlling the deployment of different types of models. The alternative solution, of course, is trying to wrap everything into a single model that it serves as the single point that makes all final decisions. Everything feeds into a single ensemble. The problem with doing that is that you create only a single on-ramp for changes to be made. It's kind of the same as the decision of whether or not you want to have a system that's filled with microservices or a system with a monolith. A monolith is easier to maintain as a small organization where you're trying to not to go with the overhead associated with lots of different services, but it's also much harder for many people to be able to make different kinds of changes to at the same time. Utilizing lots of smaller models all federated together into a simpler or ensembling system enables engineers to make changes and improvements to smaller parts of the system independently. At Twitter, I worked with a lot of different teams that were working with different kinds of model deployments, and very often I found that the single model approach would freeze progress because the amount of work and efforts required to make an improvement to the model requires you have to shut the previous model down and turn on your new one. And so that's a very, very large and heavy process filled with humongous amounts of operational burden and validation burden. Whereas when you have a very, very small thing, when you can we'll turn things off when the precision gets low, we'll add new things if it's unique precision added is much higher. Being able to make incremental improvements is much faster and easier. And so that's one of the reasons why we're opting for this more federated architecture, to be able to enable different engineers, different parts of the team to make incremental improvements by themselves.
That's really cool. I obviously like the microservices versus monolith has been an ongoing debate. Anybody who logs into Hacker News once in a while, there's always one thread at least one day that has to do with complaining about one or the other. I hadn't really thought about that when it comes to like model management. But one thing that you said stood out to me, which is you mentioned like some models contributing to like complexity or overhead, or requiring sort of a lot of thoughtful care effectively, and then sort of the long tail of everything else where you've got some monitoring on it. As long as the monitoring isn't throwing off any alerts, you just sort of assume that it's okay. And to borrow a phrase from like DevOps or from SRE, you treat those models like cattle, not like pets. And then those like high complexity models, those are your pets, and you got to kind of pay attention to them a little more closely. Is that an accurate characterization of like the way that you treat them?
Yeah, I think it is. I mean, and I think that one of the keys to this is being confident that they actually are cattle and they don't need to be treated like pets. That you need to have the appropriate monitoring in place in order to know when their precision is going down, or when they're no longer performing up to snuff. The Ultimately for us, it a lot of it comes down to what we're relying on models to do. In a lot of ways, it's really just two things. One is to flag enough things uniquely so that it's contributing to our overall performance of the system, and the other is to flag things with high precision so that they're not creating false positives and creating customer pain. And as long as those two things are true, then we're able to feel confident that something is performing well. And so we have a centralized process for understanding and evaluating how well these two metrics maintain their performance at the level of each of the individual detectors that we deploy. And so that lets us understand which models need to be treated like cattle and which need to be treated like pets. And this is very, very constant over time. There's many, many models that are remain unchanged for a year. Usually what will happen is we'll launch a model. It will have some amount of performance. If it is a cattle model, it will slowly degrade over time, over the course of perhaps 6 months to a year, until eventually it reaches the point where enough other better things have been launched that we can bring it off and send it to be turned into steak.
I've never heard of a model turning into steak, but there's a first time for everything. So the monitoring that you're applying, I assume you have some sort of a basic, like a template or a rule book. This kind of becomes systematic at this point, where for example, you mentioned precision. So like we're going to track precision of the model over time, or we're going to track some other characteristics on an ongoing basis. And then is it just there's some sort of a threshold or some sort of a basic indicator that says like, hey, somebody needs to possibly decommission this model or spin it down, that kind of thing?
Yep, that's right. So basically, we have like a guideline for what's the unique contribution of any individual detector that it needs to be able to maintain in order to stay live. And so that's just directly measured in terms of precision of this. If this is flagging things and nothing else is flagging things, what is the precision of the things that this is uniquely flagging? If this is uniquely flagging things with really, really low precision, then someone needs to look into that. Sometimes we'll need to keep things like that on because they're flagging really, really valuable and important things. And often when you have something that's flagging really, really valuable and important things, but it has really, really low precision, that's something you need to take action on, either to increase its precision, to get something else that has higher precision to start flagging those important things so we can turn this off. There's a couple of different ways that goes about. But as long as the set of things that this is flagging uniquely has high precision, and we're not worried that this was previously flagging lots and lots of things and now it's flagging fewer things, and so we're going to be missing things that this was previously flagging, then there's no reason to uh, allow the complexity of this individual thing to override complexity that we need to pay attention to.
Got it. So monitoring that brings human attention to say like, okay, it's time to go and evaluate this and decide. And it may be that once somebody on your team actually looks into it, it may be either or, and you can take appropriate action from there.
Yep. Yeah.
So,
Yeah.
Dan, I want to make sure that we get a chance to talk about one topic. You've spoken in the past about what you phrase as resilient machine learning, and that at least sounds related to these types of processes that you just described. Can you tell us a bit more about what is resilient machine learning? How's that related to what we just talked about?
Yeah, absolutely. So resilient machine learning is the design of machine learning systems that are capable of handling the kinds of challenges that software systems often experience, whether it's catastrophic failures in terms of features suddenly disappearing, services going down, data distributions changing, or softer, slower failures like the onboarding of new customers or new kinds of users, whose behaviors are very, very different than what's been seen in the past. And so designing resilient machine learning systems requires anticipating what is the set of possible changes and possible stresses that your system may go under, and testing your system so that it is resilient and you understand how it will behave in these kinds of settings, and making design decisions with your machine learning models and with the deployment of your machine learning models so that you're confident that your models and systems will be able to perform well and not catastrophically bad when these problems inevitably occur.
And maybe this is sort of implied. It sounds like there's some degree to this. Like if you're designing machine learning systems with resiliency in mind, that they're sort of blind. They could be blind to these types of problems. The problem can occur, and the model can just continue to work at some level of reliability. Is that correct, or is monitoring also a piece of the resiliency strategy, or how does this actually work in terms of a working system?
I would say that they're complementary rather than being closely tied to each other. I think that one of the federated design of our system is intended to be a element of resiliency, that in order to be able to support operation on very, very different kinds of customers, very, very different kinds of attacks. And one thing that we need to think about a ton is cyber attackers coming up with new kinds of attacks. This happens every day, and the efficacy of our product is determined not by how well we can catch attacks that have happened in the past, but how well we can catch attacks that will happen in the future. So we need to be resilient to those kinds of changes in data distribution that are adversarially selected based on what attackers have seen work in the past. And so that kind of adaptability is key. But of course, there's also certain types of signals that are not available in certain customer environments or in certain types of changes. And we also need to be resilient when services go down. And so the federated design allows us to build and ship detectors that rely on very different kinds of signals. So some rely on signals that are easy for attackers to spoof, some don't. Some are only rely on signals that attackers have no control over, or that are not as susceptible to feature serving failures or customer distribution changes. And so this federated design is built to exploit the different kinds of, or anticipate the different kinds of resiliency and be execute detection in a way that is resilient. But this federated system requires having a lot of monitoring built into play in order to support it. So in designing a resilient system requires making design decisions that are very monitoring heavy in terms of what types of metrics we need to be able to track and how we need to be able to track them.
Got it. Okay, makes sense. I do want to get to the rapid fire questions before we close out the episode. But before that, if people want to learn more about resiliency in machine learning or hear more from you on this, like what's the best way for people to find out that information?
Well, I have a post on my website, danshiebler.com, where I've written a little bit about it, and I'm always open to people reaching out on LinkedIn as well.
Okay, great. So we'll include a link down below in the description to Dan's website so you can get in contact with him there. I think it's a fascinating topic. I think about it a lot in terms of other systems as well. I mean, we would expect to see resiliency in like physical infrastructure. We would expect to see it in like data pipelines or things like that. So seeing it applied in machine learning is exciting. Yeah, I'm definitely going to go check out the website. I'd love to go deeper on this. I hope we get to talk again about it soon. But that said, you ready for some rapid fire questions?
Shoot.
Okay. Number one, what is your favorite word?
Majestic.
Majestic. Okay, that's good. Number two, favorite history podcast?
History of Byzantium.
Of Byzantium. That's a specific podcast all about Byzantium?
That's right. I really like Byzantium.
Okay, very cool. We'll have to link to that down below as well. I'll interject. I've been listening to Dan Carlin, which I enjoy, but I haven't heard of Byzantium. I'll have to check that out. All right. Last question, Dan. What's one subject you wish you could learn more about?
Probably philosophy.
Okay, that's a good one. That's a thinker. Great. Well, Dan, it's been awesome having you on. We talked about resiliency and machine learning. We talked about threat detection models. We talked about managing a portfolio. of a large number of models and what's involved in doing that successfully. We obviously heard a little bit about Abnormal and what you guys do in the security space. It's been great to talk with you. Thanks for being on the observatory today.
Absolutely. Thanks, Kyle. I had a great time.
Awesome. And we'll see you all next time on the next episode of the Observatory. And check the description down below for links to Dan's website, the podcast we mentioned, and a few other things. And we'll catch you next time on the next episode of the Observatory.